Today we're digging into a really foundational paper that, honestly, tackles one of the biggest bottlenecks in modern LLM development, just getting your data right. The paper is DataFlow, an LLM-driven framework for unified data preparation and workflow automation in the era of data-centric AI.
And it's so critical because the way things are done now, as the authors point out, is, well, it's a mess. It's all just a collection of ad hoc scripts.
Right, which completely kills reproducibility, and it just doesn't scale, especially now that we're trying to use models to help generate their own training data.
Exactly. So DataFlow's proposal is to fix this with a unified, extensible framework. They've built up these system-level abstractions with, I think, nearly 200 reusable operators.
The key thing that caught my eye was the PyTorch-Style API for building these pipelines. They're basically trying to bring some much-needed standardization to the data side of things.
They are. And the results they show are pretty compelling, especially on data efficiency. They consistently get better downstream performance across 6 different domains. But here's the headline number, the one you really need to hear. They created a small, unified data set of just 10,000 samples using DataFlow.
Okay.
And with that 10K data set, they enabled base models to actually surpass similar models that were trained on 1 million instances of generic data, like Infinity Instruct.
Wait, hold on. 10K beats 1M. That's a wild claim. What are some of the specific gains? How do they back that up?
So for something like Text-to-SQL, they saw up to a 3% gain in execution accuracy over a massive data set called SynSQL. And on the really tough math benchmarks math, GSM-8K, they're seeing solid 1 to 3 point gains.
So the takeaway is that this is really about establishing a new, more reliable standard for building high-quality data.
That's the mission.
All right, let's unpack this whole system. We should probably start with the problem itself, what they call the fragmentation problem. We all get that data quality is key, but what makes today's data pipeline such a mess?
I mean, the pipelines themselves have just gotten so much more complex. It's not just about scraping data anymore.
Right.
You're doing synthetic generation, then you're refining it, filtering it, evaluating it. It's this whole multi-stage process. And because there aren't any principled abstractions for this.
Everyone just writes their own scripts.
Everyone writes their own scripts. And that's where the technical debt just piles up.
Oh, absolutely. Anyone who's tried to run a data script someone else wrote 6 months ago knows that pain. It's always just a couple of dependency updates away from completely falling apart.
Exactly. It makes these pipelines basically impossible to reproduce, hard to build on, and you can't even reliably compare what you're doing with what another team is doing.
And this whole mess is getting worse because of a pretty big shift in how we even think about LLMs.
A huge shift. The idea that LLMs aren't just consumers of data anymore.
They're becoming the producers.
Yep. They are powerful data producers. I mean, the research shows again and again that really high-quality synthetic data can often beat human annotated data. So these generative model-in-the-loop workflows are becoming essential.
Where the model is basically helping to curate its own training set.
Right, but our old tools, they just weren't built for that.
So how is DataFlow different from other attempts to standardize this? I'm thinking of things like Meta's Data Juicer or NVIDIA's Nemo Curator.
That's a really good question. Systems like Nemo, Curator, and Data Juicer, they're mostly about extraction and filtering. Their main job is to clean up massive web-scale corpora for pre-training.
So cleanup.
Cleanup and curation, yeah. DataFlow kind of shifts the focus. It elevates LLM-driven synthesis and refinement to be a first-class programmable thing. It's less about cleaning up a massive pile of data and more about intentionally constructing a high-quality data set from the ground up.
Okay, so to support this, this construction paradigm, the authors lay out 4 key requirements for the system. What are they?
So first, you need these fine-grained composable operators that are specifically for generation and refinement. Second, you need explicit, verifiable pipeline definitions.
Like a protocol.
Exactly, an open source protocol. And they use torch.nn.module as their benchmark. They want to do for data prep what PyTorch did for model building.
That's a powerful analogy, making it immediately familiar to ML engineers. What about flexibility?
That's number 3. The whole system has to be back-end agnostic. It shouldn't care what LLM serving engine you're using or where your data is physically stored. And fourth, looking ahead, it has to support agent-driven automatic workflow construction.
To make it easier for people to actually use it.
Right, to lower that engineering barrier.
That's a perfect lead into the architecture. Let's get into how they actually built this. The core idea was about the developer experience, right? Keeping it simple.
Precisely. They made a very conscious choice to avoid things like complex YAML files. They wanted a PyTorch-like interface that's instantly friendly to your IDE and just feels natural to most ML developers. The goal is one unified way of doing all these different data prep tasks.
So let's start with the foundation. They talk about this global storage concept. Why is having a centralized canonical data representation so important?
Because in these complex pipelines, the biggest headache is just managing the schema and keeping everything consistent. So DataFlow has this global storage that maintains one canonical tabular representation of your data.
So columns for instructions, responses, chain of thought traces, scores, all that stuff.
All of it. And it uses a really simple DataFlow storage class with just basic read and write operations. And that abstraction is so vital because it completely decouples your operator's logic from the physical storage layer.
So the operator doesn't care if the data lives on a local disk or in some distributed cloud bucket.
It has no idea, and it doesn't need to.
That's smart. Okay, but if storage is decoupled, the LLM part has to be just as robust. Tell me about the LLM Serving API.
So this is the single front door for any LLM call, an API called Generate from Input. It's designed to handle all the messy details transparently.
So whether I'm hitting a fast local engine like VLLM or making a call out to, say, the Gemini API.
The serving layer manages it. It handles batching, routing, rate limiting. All of that complexity is hidden from the person building the pipeline.
But doesn't that just move the complexity? I mean, managing authentication, versioning, and rate limits across 5 different backends sounds like a nightmare for one API to handle.
It is complex for sure, but the point is that it hides that burden from the pipeline developer. The person writing an operator doesn't have to worry if OpenAI is rate limiting them or if VLMM is about to run out of VRAM. They just make the call.
And that centralization is what makes the whole workflow reproducible across different setups.
Exactly. It's key to delivering on that PyTorch for data promise.
Okay, so storage and serving are centralized. What about the actual transformation units, the operators? How are they designed to be so composable?
They follow a very clean design. All the configuration happens in the init method, and the actual work happens in the run method. And they only talk to that central storage through key-based bindings.
So they specify input keys for the columns they need to read and output keys for the new columns they're going to write.
That's it. And that clean separation between configuration and execution is so important. It lets the system do a static analysis of the whole pipeline before running a single expensive operation.
Right. It keeps the operators themselves very lightweight. And I saw they also have this idea of prompt templates.
Yeah, and decoupling the prompts from the operators is a really powerful move.
Why is that separation so important?
It basically lets you encapsulate reusable prompt patterns. Think about that text-to-SQL task. You can have one single SQL generator operator, right? The core logic is the same. But by just swapping out the prompt template...
You could have it generate SQL for my school, then Squy, then something else, without touching the operator's Python code.
Exactly. It makes the whole library way more useful.
So you string these operators together into pipelines, which are basically just sequences or directed acyclic graphs.
Right, which just means it's a defined sequence of steps that always moves forward. No infinite loops in your data processing.
And this is where that compile step you mentioned comes in. It's like a pre-flight check for the data pipeline.
That's a great way to put it. It does a static analysis, checks dependencies, makes sure you're not trying to use a data column that hasn't been created yet, and then it produces the final execution plan. It saves so much time and GPU cycles on debugging.
So with nearly 200 of these operators, how did they organize them all? They came up with this GEFR paradigm.
Right, the Generate, Evaluate, Filter, Refine model. It's the skeleton for all their main template pipelines.
So break that down.
It's simple. Generate operators add new data. Evaluate operators compute scores or labels, like a quality score. Filter operators remove rows based on those schools, and refine operators just modify existing fields, maybe cleaning up text or removing PII.
So your dataset size grows during generation, and then it shrinks during evaluation and filtering.
Exactly. It gives you this very explicit, very verifiable control over the quality-quantity trade-off.
Let's talk about the automation layer, because for a lot of people, this might be the most exciting part. The DataFlow-Agent. Manually building these pipelines sounds hard.
It can be. And that's what the agent is for. It's designed to take a user's natural language goal and turn it directly into one of these executable pipelines. It's actually a pretty sophisticated multi-agent system built on LangGraph.
So how does it handle a user's, vague request?
It starts with an intent analysis agent that breaks down the query into smaller, actionable steps. Then it goes into a planning phase where it checks its library of operators to see if it has the tools it needs.
But what if it doesn't? What if a user wants some novel function that isn't already in the library? This is where a lot of these agent systems tend to fall down.
And this is DataFlow-Agent's key differentiator. It has what they call an operator synthesis agent. It follows this retrieve, reuse, synthesize strategy. Meaning if it finds a gap, it actually uses RAD to generate new Python code for a brand new DataFlow operator. And this is the critical part. It then runs automated unit tests on that code it just wrote, debugging it until it's a verified working component.
Wow. Okay, so it can synthesize and automatically debug its own tools. That's a huge step for making these agentic workflows actually practical. The system can expand itself.
It's a massive leap. And then once the full pipeline is assembled, the pipeline verification agent takes over. It runs the whole thing in a sandbox with mock data just to check for any runtime errors before giving you the final validated plan.
So how well does this actually work? Is it reliable?
It's pretty good. When you give it clear specification, it scores in 0.80 overall accuracy, which is solid. But the evaluation also shows the limits of where we are with complex reasoning.
What happens on harder tasks?
On tasks, they labeled hard, so underspecified things where the agent has to infer a lot. The performance drops quite a bit, down to 0.23 accuracy.
So it's great for automating the assembly of known parts and can even build simple new ones. But for really ambiguous, complex problems, you still want a human in the loop.
That's the realistic takeaway for now, yeah.
Okay, let's pivot to the results, because this is where that whole philosophy of quality over quantity really gets proven out.
It really is. The proof is across all these different domains. Let's start with the text-to-SQL case study. This is a domain where you need incredibly precise, executable data.
What were the key operators in that pipeline that really drove the quality up?
Well, the pipeline was very targeted. It had a SQL generator that was guided by different complexity levels. It had a SQL augmentor with 6 different strategies to create more diversity. But the absolute killer app was the SQL execution filter.
The quality gate.
The absolute quality gate. It runs the generated SQL and instantly throws out anything that's invalid, incorrect, or just runs too slowly. It guarantees only high-fidelity examples make it into the final training set.
And the efficiency finding here was pretty nuts, right?
It was striking. Their DataFlow Text-to SQL 90K dataset, so 90,000 samples achieved performance that was comparable to the massive SynSQL dataset, which has 2.5 million samples.
So they got the same results with, 27 times less data?
27 times less data. And when they used this DataFlow data to train a Quinn model, they boosted accuracy on a tough benchmark by almost 32 points. It's huge.
And we see that same story play out in math and code, don't we?
Absolutely. For math reasoning, the pipeline is all about synthesizing perfect reasoning traces. They start with good seeds, use a MathQ verify filter to ensure the answer is actually correct, and then generate a robust chain of thought explanation.
And the performance.
Again, top of the class. They trained a 32 billion parameter model on just 10,000 of these DataFlow samples, and it got the highest average score among all models trained on that data size. It clearly beat the other synthetic baselines.
And for code data?
Same idea. The pipelines are built to generate execution-grounded signals. The code has to actually run and pass tests. Their DataFlow Code 10K dataset consistently outperformed big instruction sets like Code Alpaca, giving them, for instance, a 7% average boost on one of the Quinn models. The story's just so consistent.
Okay, so the final stress test is to combine all of this. Section 5 talks about the DataFlow Instruct 10K corpus, where they mix the math, code, and text data to see if they can efficiently build a powerful generalized model.
This is the ultimate proof of the data efficiency concept. They fine-tuned a base 7 billion parameter model on 2 different sets. First, their 10,000 DataFlow samples, and second, for comparison, 1 million samples from the generic Infinity Instruct dataset.
So a 100x difference in the amount of data. How did they stack up?
Not even close. On the MathAv score, the model trained on 10K DataFlow samples gets a 46.7. The one trained on 1 million generic samples, it gets a 33.3.
That's a massive gap.
A massive gap. And it was the same story on code benchmarks. The small, high-quality dataset delivered the best performance.
So this tiny, carefully constructed data set let a base model get surprisingly close to the performance of its much more expensive, fully instruction-tuned version.
Exactly. In math, it closed the performance gap down to just 3.1 points. It's definitive proof that this pipeline-driven approach gives you incredible data efficiency. It shifts the work from, warehousing massive amounts of data to just engineering a really smart workflow.
So when you step back from all the details, what's the biggest implication of this work for you?
For me, it's about standardization and reliability. DataFlow is trying to provide that robust standard foundation for what people are calling data-centric AI. It's a real shift in focus from how big can we make our data set to how good can we make our data set using these composable, model-driven pipelines.
And the authors are definitely thinking bigger than just text.
Oh, absolutely. The conclusion makes it clear they see this expanding. They talk about a Dataflow ecosystem, mentioning things like Dataflow table, Dataflow graph, even Dataflow multimodal. They're positioning this as a foundational layer for all kinds of data-centric AI.
So the paper's ambition is for Dataflow to become the PyTorch for LLM data preparation. And that raises a really interesting question for you, our technically minded listener, as you're thinking about your own work. If we can get this kind of performance with 10,000 samples instead of 1 million, does this signal that maybe the next decade of AI innovation won't be dominated by wild new model architectures, but by standardized, efficient, and reproducible data workflows? Something for you to consider.